Hi guys, this is for Module 8.1, Perpendicular Bisectors of Triangles. Now, our essential question is how can we use perpendicular bisectors to find a midpoint that is equidistant from all the vertices of a triangle? Now, we've learned what perpendicular bisectors are, okay? So we have 2 points on a line segment, for example, okay? A, point B, and then we draw a line cutting across. And this line represents our perpendicular bisector. We'll call it line L. Now, by definition, perpendicular bisectors, basically the distance from line L to A are congruent to the side or from the point B to line L. Now, any point on that line, that perpendicular bisector, is going to be equidistant from the 2 points of that line. Okay, so the distance from, we'll call this point C, okay, which is on the perpendicular bisector, is going to be equal distance from A and B, okay? And if you notice, I accidentally, or in showing you this example, I ended up drawing a triangle. So that just kind of comes with the territory of the definition. So remember, equidistant means equal distance. All right, so our answer is basically we can find the equations for at least 2 of the 3 perpendicular bisectors of the sides of a triangle. And we've talked about parallel and perpendicular lines, so that kind of kicks in with the formulas. The circumcenter, again, circumcenter is a key word in today's lesson, so make sure you understand what circumcenter means by the end of the video, which is the point that is equidistant from all the vertices. Okay, so basically it would have to be um, a point, let's say here, okay, on my little example here, and it's equal distance from all 3 points. This would be considered your circumcenter. You know, like if you were to build what is it called? An amusement park. It's a good example. Between city A, B, and C, you would definitely want it to be equidistant. That way, not one city is complaining about being too far away. Now it's located at the intersection of any of the 2 of the perpendicular bisectors, and we're going to show that as an example. So remember, perpendicular bisectors is a big key part of the video as well. All right, so constructing a circumscribed circle. So there's some definitions we need to be aware of. A circle that contains all the vertices of a polygon. Basically, if you see the circle around the triangle XYZ, a vertex X is on the circle, as is Y, as is Z. Now, that is referred to as a circumscribed polygon. All right, so XYZ, triangle XYZ, is actually considered to be circumscribed. It exists within that circle. Now, in the figure, circle C is circumscribed about triangle XYZ. So, if we look here, a circumcircle, all right, is basically a circle that contains all those vertices, and its center is at point C, which is what we call the circumcenter, okay, which is actually the circumcenter of the triangle in the first place. And what's good about that, again, if you were to build a theme park, you would definitely want to create that theme park at that circumcenter, just because it would be equidistant from all 3 cities, which is good for profit margins, etc. All right, so now construct the circumcircle of triangle PQR. Now what you've already noticed in the cutouts is you don't have this pretty picture, and you do need this compass. All right, so scrounge around. Let's find some. And basically I want you to draw a circle. All right, draw a circle, maybe a couple inches, maybe an inch, inch and a half in the radius. Okay, so from here to here, probably an inch, inch and a half. Okay, and that should be enough of your radius to draw your circle. So draw your circle, and then what I want you to do is I want you to create 3 vertices that exist on that circle. And with that, you're going to draw a triangle, a polygon, a circumscribed polygon, okay? A triangle, if you will. Again, circumscribed means it exists on that circle. So the center of the circle must be equidistant from all 3 points, okay? And we don't know where C is unless you're using a compass. That's why you need this. Okay, so if you drew your circle, you should notice that you put the pointy end, okay, this guy right here, on somewhere on your paper. That's going to be your point C. Okay, so this represents your pointy end of your compass. So you drew your circle first, okay, then you labeled your 3 vertices, you drew your triangle, okay, make sure you're using pencil in case you mess up, and then basically what I want you to do with your compass is you're going to use the same radius, okay? So you're going to start on one of your points. Let's say point Q, okay? Put your pointy end, okay? So by now you should have your circle, you should have your triangle that's circumscribed, and I want you to put your pointy end on point Q, all right? And then what you're going to do is you're going to use the same radius, the 1.5 inches, okay? And you're going to draw this arc. And once you draw this arc, you should see something like that. Then I want you to put your pointy end of your compass on point R, okay? And with the same radius, 1.5 inches, I want you to draw your second arc. And it should look something like this. Now, with the straight edge, you're going to draw a line. This line right here. You should have successfully created a perpendicular bisector. Double check with the protractor. If you were to measure this angle right here, you should get 90 degrees, okay? So once you do that, you should see something like that so far. Now the next thing I want you to do is I want you to, here I'll write this part in purple, I want you to put the pointy end of your compass on P. And with the same measurement, 1.5 inches, okay, on your compass, is I want you to draw another arc, okay? So it's around there, okay? Should, and then once you do that, pointy on point R, and draw your next arc. Again, make sure you're keeping your compass at 1.5 inches in distance from the pointy to the pencil part of your compass. And you should successfully draw your second. Again, you only really need 2 perpendicular bisectors to find your circumcenter. So again, you should be drawing this line right here. Again, measure with a compass or a protractor, and double check, make sure you're at 90 degrees at your angle. There we go. So just make sure you're at 90 degrees for that angle as well. Now, if you do the arcs correctly, if you draw the arcs correctly, again, 1.5 and all that jazz, all right, and 1.5 inches in distance, double check your 90 degrees. If you did this right on your protractor, or I'm sorry, your compass, again, the compass is the object to the right, you should notice that they intersect, okay, at a certain point. That point is your circumcenter, okay? That should be your point C. Once you have that, label it and you should see it. Now, what that means, okay, and I'm going to go ahead and read out the rest of this. So the set of points that are equidistant from Q to R is called the perpendicular bisector of QR. So that was one of the things that you had to draw first. So let's say that's your perpendicular bisector. We'll call it L. We use a compass and a straight edge to construct those points. So hopefully you had a ruler, okay, and a protractor would work. So you probably also need a protractor just to make sure your 90 degrees is there. Now the center must also be equidistant from P to R, and the set of points that are equidistant from P to R is also called a perpendicular bisector. So that's something you had to draw. Okay, again, your credit today for notes. I'm not really going to care about much, but I'm definitely going to be looking at this drawing. Okay, it's that's the main standard for any kid in geometry is know how to draw something like this. So we use a compass, a straight edge, and we do that. Now, once you notice the intersection between your two perpendicular bisectors, we'll call them L and M, you should notice this point C. Now, point C, again, is the middle of your circle, all right? So it's the circumcenter. So again, once you have this drawing, double check with me. Make sure you measured your 90 degrees. And if you did this correctly, you should notice that the distance from P to C, this is the main idea, P to C is going to be the same or congruent to the distance from C to R, and the distance from Q to C are also going to be the same. So I want you to measure those, and I want you to give me the measurement, okay? Give me, it's going to be in inches, right? Give me the measurement of that P to C, C to R, okay? And it's going to be in inches, and then Q to C. Give me those measurements. Measure with a ruler, okay? So I can see. That way you understand that you actually successfully drew something that is equidistant from all your vertices, okay? That is the circumcenter. All right, so proving the concurrency of triangles perpendicular bisectors. Now, three or more lines are concurrent, sorry, if they intersect at the same point. So if you look at AP and BP and CP, they're all concurrent because they intersect at point P. That is known as your point of concurrency, all right? So basically, you have multiple lines all intersecting at that certain point. Now, we played around perpendicular bisectors when we were constructing our circumscribed polygon and our circumcenter and all that jazz. Now we got to prove this. So if we look at the theorem that's involving this theorem, and I already mentioned it earlier in our construction, all right, when you measured those three lengths, you should have realized that the distance of from here to here should be the same as the distance from here to here and here to here, okay? So that's equidistance. And that's what the theorem is saying, is basically if the perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the vertices of the triangle, basically what's going to happen is you're going to have three lines, okay, that are all equal to each other. That's the idea. So this is basically all this theorem is saying. So if you have perpendicular bisectors, which we do, okay, here's one right here, 90 degrees, here's one right here, 90 degrees, here's one right here, 90 degrees, you're going to have three lines being congruent to each other. So here's the proof. We have lines L, M, and N. They are perpendicular bisectors. Wonderful. So we got 90 degrees here. Here's line L, 90 degrees here. And lastly, here's our perpendicular bisector with 90 degrees right there. Now, obviously, this isn't drawn to scale too well. All right, now basically, P is the intersection of L, M, and N, so it is acknowledging that P is our point of concurrency. So let's see, P is the intersection of L, M, and N, since P lies on the, again, perpendicular bisector of AB. Now, PA is going to be equal to PB by the perpendicular bisector theorem. So if we look at what I mean here, PA is right here, and that's got to be equal to PB right here, because when you do this whole perpendicular bisector things of AB, just on the, like the original example I drew you, you know that these two should be congruent to each other, those two segments. should be congruent to each other because of the perpendicular bisector theorem. Now, similarly, P lies on the perpendicular bisector of BC. And again, here's BC, all right? And then we know that P lies on the perpendicular bisector, which is this guy right here, okay, BC. So we know that PC should be congruent to PB. Therefore, by the transitive property, PA equals BP, which equals PC. So notice how we started. This guy and this guy are congruent. Sorry. That's what I'm stating right now in this proof. Is I'm saying, let me try a different color. There we go. Basically, AP has got to be the same as this guy because that's a perpendicular bisector theorem. And since we have a perpendicular bisector between BC, PB is going to be congruent to PC right there. All right. So using properties of perpendicular bisectors. So we get this lovely image here. And now they're saying KZ, LZ, and MZ are all perpendicular bisectors. That makes sense because they all have those 90 degrees, right? So that's like a good heads up. One of the things I like to do is once I see that whole idea of perpendicular bisectors, I'm thinking about the theorem itself, which basically says this right here, that the length here. Oh, and note, it's not drawn to scale. All right, so some people, they try to measure it with a ruler right away, and that can lead you astray. It's like a geometry version of a mirage. Okay, so basically, I'm thinking this, or this, but that's not the case. Let me see here. Let's see what they give us in this example. So ZM equals 7. Okay. ZJ is 25. And HK is 20. HK is 20. All right, find ZH. Okay. Now, one thing's for sure is if we have those perpendicular bisectors, that means HZ has to be congruent to GZ, and GZ has to be congruent to ZJ. That means HZ has to be 25, okay? So again, ZH equals 25 because ZG equals ZH, which equals ZJ. All three of those guys are congruent because Z is equidistant from those three vertices. Now, ZJ, they said it was 25. Now, K is the midpoint of GH. So this guy is in the middle. So we know that KH has to be congruent to GK. And if we're going to find HG, okay, that means the whole side here, we know that makes two 20s, right? Because we know those two distances have to be the same. So GH has to be 40. So again, HG should equal 40. All right, so we're going to change it up here. Okay, so hopefully you got everything down from that problem, because I'm going to erase up here on my work. Now I'm going to start off with another example. Okay, part B. So let's start with what was given. ZH is 85. Ooh, big numbers. ZH is 85. Okay, that's a 85. Okay, and then MZ is 13. And then HG is 136. HG, again, this whole segment right here is 136. And now we have to find KG. Okay, so KG is right here. And again, they told us these guys are perpendicular bisectors. That means this guy has to be the same as this guy, right? So HK has to be congruent to KG or GK. So what's half of 136? I'm getting a 68 here, okay, I think. 13 divided by 2, 6, remainder 1, 16. 16 divided by 2 is 8. So yeah, we got 68 and 68. All right, so that means KG has to be 68 degrees, 68, okay? Now K is the midpoint, okay, of HG, and that's something I had to realize at first. KG equals 68. HG, again, is 136, and basically what I did is I just halved that, okay? So I should have gotten 68, yeah. Now Z is the what of triangle GHJ. Z is the circumcenter, okay, of that triangle. All right, so ZG has to be congruent to HZ and has to be congruent to ZJ. All right, so that's something to notice. So again, ZJ is congruent to ZG is congruent to ZJ, and ZJ has to be congruent to ZH or HZ. Okay. So if ZH equals 85, which they gave us, ZJ also has to be 85. So we just found our second thing they were looking for. All right. So here's your turns, okay? Again, they tell us that KZ is a perpendicular bisector, as is LZ, as is ZM. So it's just like the example I gave you on the last slide. Basically, you're going to have your givens, all right? And then they're asking you to find certain distances. So again, they give you givens, and you have to find what they're asking about. So again, this is your turn number 1 right here, your turn number 2 right here. Same process as my examples from earlier. All right, guys, have a great day. If you have any questions, let me know. Good luck with those compasses. If you're having any issues, just come see me.